All right, we are in section 5.4, talking about the definite integral some more and how it relates to area. So if f of x is a continuous non-negative function on the interval from a to b, we say that the area under the function and above the x-axis on this interval is exactly equal to the definite integral. So this area is equal to the integral from a to b of f of x dx. So we can use integrals to interpret areas under a function, under a curve, and above the x-axis. This is why it's always giving us a numerical value. That numerical value is that area. But if a graph of f of x lies below the x-axis, then the area between f and the x-axis is negative. So when we talk about the idea of area with an integral, we're not talking necessarily about geometric area, because if it was geometric area, everything gets counted positively no matter where it is. But what we have in this case is what we would call net area. So this would be called net area, where values above the x-axis are counted positively, but values below the x-axis are counted negatively. So we can see the integral from a to b of f of x dx would be a1 minus a2, where a1 is the area under the curve and above the x-axis, and a2 is the area below the x-axis above f. So like in this particular diagram right here, that's a1, that's the positively counted areas, and then down here would be a2. Now the nice thing for us is that the integral is already doing this. This isn't something that we need to like take extra steps for or precautions for. Integrals are already giving us net area. They're counting those positive areas and negative areas and adding them together. So we can look at this visually before we get to any antiderivative calculations. Evaluate the integral from 0 to 3 of x minus 1 dx by interpreting as area. So if I go ahead and graph, with a function like x minus 1, this is one we could actually do geometrically and using physical area to calculate the integral, because this function is a little easier to work with. So we're on the interval from 0 to 3. So 0 to 3. And we have a slope of 1 and a y-intercept of negative 1. So that's going to go up 1 over 1. Something right about there. That's not too bad. A little bit farther. There we go. So this will drop down right here. Right there. So we're going to have two different areas here. We're going to have this area down here and this one up here. So now when it comes to counting these, we're going to have our area down here. I'll call this one A1 just because it comes first, but it doesn't really matter what you call them. I'll call that A2. So when we're calculating to find the area of A1, we're going to get the area of the triangle is 1/2 base times width. So that's going to be 1/2, or base times height, I guess. 1 times 1. So that's an area of 1/2. And then A2, that has a base of 2 units and a height of 2 units. So 1/2, 2 times 2. So that's 2. So our area, our total area under the curve, which is the value of the integral from 0 to 3, is going to be the positive areas minus the negative areas down here. So we're going to have 2 minus 1/2. So that's going to be 3/2. And if we wanted to do this on our own, so just as a side note, we could absolutely evaluate the integral here. So that's 1/2 x squared minus x from 0 to 3. That's 1/2 times 9 minus 3, and then minus a bunch of zeros. So 9/2 minus 3 is 9/2 minus 6/2, which is 3/2 also. So we would get the same value, but obviously we're trying to draw a connection here between the integral and the area itself. Now, most functions, especially in calculus, you're not going to be able to do geometric interpretations like this. This one just works out really well in our favor because it's a straight line. Most functions will require the use of an integral and an antiderivative. So let's take a look at another example at the top of the next page here. So we're going to evaluate and compare these two integrals. So notice they have the same integrand, they have the same function inside of them, but their bounds are different. So let's get the first one. So we're going to take the antiderivative, so that's 1/3 x cubed minus x, evaluated from 1 to 2. So that is 1/3, 2 cubed is 8, and then minus 2, minus 1/3 times 1, minus 1, so that's 8/3 minus 2 minus 1/3, and then plus 1. So let's see, this is 8/3 minus 6/3 is 2/3, minus 1/3 minus 1 is negative 2/3, so plus 2/3. So we get 4/3 for this one. Now if we evaluate part B, the antiderivative is the same, but now we're evaluating between different bounds. So we're going to have 1/3 times 1 minus 1 minus the negative 1 case. So 1/3 times negative 1 minus negative 1. So that's 1/3 minus 1, so negative 2/3, minus negative 1/3 plus 1, so positive 2/3, but then it's minus that. So we get negative 4/3. So we got the integral from 1 to 2 of this function is 4/3. The integral from negative 1 to 1 of this function is negative 4/3. So I have the graph here already for us. So here we have negative 1, 1, and 2. So part A was asking us the value of the integral from 1 to 2. So that's this area right here. So this is what we found in part A. And then part B was asking us from -1 to 1. So you can see the function itself is down below the x-axis. So that is our area for part B. So what this is telling us is that these two areas here are the same physical area, okay, or like the same geometric area, but one is above the x-axis and one below. Okay, so the physical space being taken up by these two pieces of area is the same, but one of them is above the x-axis, right, and below the curve. That's the positive 4/3 value. One of them is below the x-axis and above the curve. That's our negative 4/3. And the integral did that, of course, again, without us needing to adjust anything or manipulate anything. The integral knows to do that. Let's take a look at one more, because we've had cases where you can have, we kind of had in the first case, we calculated the positive area, the negative area, and then combined. With this one, we did two separate cases, one all positive, one all negative. But a lot of functions, it's going to be a little bit of both. So we don't need to necessarily do anything differently. We just need to evaluate the definite integral. So we're going to find the value of this definite integral. So we're going to do that by taking the antiderivative first. So we get 1/3 x cubed minus 5/2 x squared plus 4x, evaluated from 2 to 5. So we get the 5 case, 1/3 times, that's 125, minus 5/2 times 25, plus 4 times 5, minus the 2 case, so 1/3 times 8, minus 5/2 times 4, plus 4 times 2. A little bit of arithmetic goes into this, the combining of the fractions, and we end up getting -3/2, -3/2. So with this function, I'm going to go ahead and pull this one up. So if we look, we have x squared minus 5x plus 4. And we are on the interval from 2 to 5. So this is our function. And we're going from 2 to 5, so you can see in the first part over here, the function is below the x-axis. So all of the area down here, between here and the x-axis, is going to be counted negatively. And all the area under this portion, from 4 to 5, is going to be counted positively. So in the end, they ended up working out to -3/2. So that means the negative area down here is slightly bigger than the positive area being counted up above. And that's what we get using the definite integral to find areas. And that brings us to the end of Chapter 5. So that is our introduction into the concept of the antiderivative, the integral, both indefinite and definite, And then, of course, kind of relating the idea of area under a curve to integration. When we come back in chapter 6, we're going to start looking at more uses of the integrals and looking at plenty of applications and modeling using these types of functions. So I will talk with you all in the next chapter.